In the previous lecture, we discussed one type of process in thermodynamics known as isothermal process. Now, recall that an isothermal process is a process in which the temperature of our gaseous closed system remains constant. So if the temperature remains constant, then the change in internal energy of our closed gas system is zero. So that means all the energy that flows into our system is transformed into work done by that system on the surroundings. So now we're going to discuss three more processes that take place in thermodynamics. And let's begin with an adiabatic process. So what exactly is an adiabatic process? Well, an adiabatic process is a process in which no energy flows into the system or out of the system as a result of a difference or change in temperature. So there are two ways by which an adiabatic process can take place. So either our closed gaseous system is very insulated, or the adiabatic process takes place very quickly so that heat cannot take place, so that energy cannot be transferred as a result of heat. So let's suppose we have our closed gaseous system that experiences an adiabatic process. Let's explore what the first law of thermodynamics tells us about an adiabatic process. So recall that the change in internal energy of our closed gaseous system is equal to the sum of the Q and the W, where Q is the heat and W is the work. Now, if we're dealing with an adiabatic process, there is no Q. The Q is zero because in an adiabatic process, there's no energy that flows in or out of our system as a result of a difference in temperature. So if the Q is equal to zero, then that implies that the change in internal energy of our closed gaseous system is equal to the work. So what that basically means is if there is an increase in internal energy of our gaseous system that is undergoing an adiabatic process, that energy, that increase in energy comes as a result of work that is done by the surroundings on that closed system. And likewise, if there is a decrease in internal energy of our gaseous system, that implies that the loss of energy comes as a result of the work done by the system on the surroundings. Once again, in a closed ideal gas system that is undergoing an adiabatic process, the increase in internal energy comes from the work that is done by the surroundings on the system. So recall that if our ideal gas system is composed of monatomic gas molecules, then the internal energy of our system is equal to the product of 3 times N times R times T divided by 2. Now notice if our internal energy increases, that implies that the temperature increases, and if our internal energy decreases, the temperature decreases. So that means if we are dealing with an adiabatic process, if the internal energy increases as a result of the work done by the surroundings on our system, then the temperature increases. And likewise, if the internal energy decreases as a result of the work done by the system on the surroundings, well, that implies that the temperature will decrease. So now let's discuss two more processes that take place in thermodynamics. Let's discuss isobaric process and the isovolumetric process. Let's begin with the isobaric process. In an isobaric process, the pressure of our ideal gaseous system remains constant. So if we plot this result on our XY axis, where the x-axis is the volume and the y-axis is the pressure, we get the following curve. So if we begin at point A1 and end at point A2, the pressure will remain constant. So from the ideal gas law, we know that pressure times volume is equal to the product of N, the number of moles, R, and T. Now, if we're dealing with a closed system, our N will remain constant. The number of moles in our system will remain constant. So if we rearrange this equation, we get the following result. The volume is equal to this ratio, which is a constant, because in an isobaric process, the pressure is constant. So this ratio, a constant multiplied by T. So we see that in an isobaric process, if the volume increases, the temperature must also increase. And if the volume decreases, the temperature must also decrease, because this quantity remains a constant. Now finally, let's move on to an isovolumetric process. So in an isovolumetric process, the volume of our closed gas system remains constant. So once again, if we plot this result on the XY plane, where the x-axis is the volume and the y-axis is the pressure, we see the following vertical line. So our x-axis is the volume and our y-axis is the pressure. So the volume remains constant as we go from some point A1 to some point A2. Even though the pressure decreases, the volume remains constant. Now, if we once again begin with the ideal gas law, we see the pressure times the volume is equal to N times R times T. Now, if we rearrange this equation and solve for the pressure, we see that the pressure of our ideal gaseous system is equal to the product of this constant, N times R divided by V multiplied by T. So once again, as the pressure increases, the temperature increases, and as the pressure decreases, the temperature will decrease. Now notice, in all these processes, and including the isothermal process, the first law of thermodynamics will hold. So whenever we're solving problems using these processes, we could apply the first law of thermodynamics. So the first law of thermodynamics holds for isothermal processes, isobolometric processes, isobaric processes, and adiabatic processes.